In Lesson 4.7, you studied arithmetic sequences, in which any two consecutive terms have a constant difference. In the Solve It, the sales prices form a geometric sequence. In a geometric sequence, the ratio of any term to its preceding term is a constant value, also called a common ratio. Consider the sequence 2, 10, 50, 250. 2 is an example of a term, 10 is also a term, 50 and 250 are the four terms shown in this sequence. Note that to get from 2 to 10, we could add 8, but adding 8 to 10 does not get us to 50. Instead, we should multiply by 5. 2 times 5 is 10, and 10 times 5 is 50. 50 times 5 is 250. That value 5 is called the common ratio. Key concept: geometric sequence. A geometric sequence with a starting value a and a common ratio r is a sequence of the form a for the first term, comma, a times r, the second term, comma, a times r squared, the third term, followed by a times r cubed, and so on. A recursive definition. We begin with our starting value, a sub 1, meaning the first term. That will equal a. And then a recursive formula is written in the form a sub n. So for any number n greater than or equal to 2, the term a sub n will equal a sub n minus 1, so we can think of that as the term right before, or the previous term, times r. Again, that's for n is greater than or equal to 2. So take note, a sub 1 equals a sub 2 equals a sub 1, the term right before, times r, a sub 3 equals a sub 2, again the preceding term, times r, a sub 4 will equal its preceding term, a sub 3 times r, and so we can see a, our initial term, times r, to get to our next term, remember r is our common ratio, equals ar, times r again equals ar squared, times r one more time, ar cubed, and the pattern continues. We can also define geometric sequences explicitly, or using an explicit definition. Well, in this case, a sub n will equal a sub 1, the initial term, times r raised to the n minus 1 power. That's for n greater than or equal to 1. So take note, a sub 1 equals a, our starting term, our initial term. A sub 2 equals a sub 1, the preceding term, times r. That should seem familiar. A sub 3 equals a sub 1 times r again, our common ratio. And that equals a sub 1 times r squared. A sub 4, working through a similar process, we find it equals a sub 1 times r cubed. So note an explicit definition is based on the initial term times the common ratio raised to a specific power. Problem 1, identifying geometric sequences. Which of the following are geometric sequences? A, 20, 200, 2,000, 20,000, 200,000, and so on. Note, to get from 20 to 200, we can multiply by 10. Multiplying by 10 again will get us to 2,000, and again 20,000. So it seems we have a common ratio of 10. There is a common ratio, r equals 10, so the sequence is geometric. B, how about the sequence 2, 4, 6, 8, 10? It sure looks like it can be an arithmetic sequence, simply adding 2 to the previous term, finding a common difference of 2, but we're looking to identify whether or not it's a geometric sequence. So to get from 2 to 4, we would multiply by 2, but when we multiply 4 by 2, we would get 8, not 6. In this case, we'd have to multiply 4 by 1.5, 6 gets multiplied by 1.33 approximately, and 8 would be multiplied by 1.25 to get 10. So there is no common ratio. So the sequence is not geometric. Part C. 5, negative 5, 5, negative 5, 5, and so on. We would have to multiply 5 by negative 1 to get negative 5. And if we multiply negative 5 by negative 1, we get back to 5. And that pattern continues. There is a common ratio. R, in this case, equals negative 1, so the sequence is geometric. Your turn. Part A. Is the following a geometric sequence? If the sequence is not geometric, is it arithmetic? 3, 6, 12, 24, 48, and so on. Part B. Same questions, but for the sequence 3, 6, 9, 12, 15, and so on. C. How about 1/3, 1/9, 1/27, 1/81, and so on. And D. 4, 7, 11, 16, 22.